Dear students, let's continue with the concept of calculus at the rate of physics. Especially related to quantum mechanics. Let us start with a simple mathematical expression. Let it be question number 1. And further, let me consider two operators, differential operators. Let me call it equation number 2, and the other operator is equation number 3. Now let me operate operator O1 on expression number 1. So it comes out to be O1 into psi, which exactly gives me del square upon del x square into 3 sine 4t minus 5x, which is exactly, if I differentiate it once, I will be getting 3 cos 4t minus 5x, and since the derivative with respect to x, I will be getting minus 5 more. Similarly, if I differentiate it once more, I will be getting minus 3 sine 4t minus 5x, and one more 5 will appear now, so I can write minus 5 the whole square. That is exactly, if you see carefully, this is nothing but psi again, including 3. This is psi, rather this is psi. So let me write it as psi again, and I come to know that minus 25, which is minus 5 the whole square, and the remaining is psi. So something like this, O1 operating on psi is minus 25 into psi. Let me call it as equation number 4. I need not to tell, it is obvious on the symmetrical ground that if I do O2 with psi, see here we got a coefficient of x twice, so then we got a coefficient of t twice. Then derivative of sine gives you cos gives you minus sine, everything remains same. Only thing is now it will be minus 16 into psi, equation number 5. This is the important relation here. My psi is same in both the cases. When I change the operator, this value is changing. Actually, these values are changing when I change the operators. That means there is some definite relation between this value and this operator. So this value and this operator. We'll have more details very soon. Let's generalize this expression something like that. Whenever you get some operator operating on psi, it's some constant into psi again, then this expression is called Eigenvalue Equation of the operator O. Remember, It's not eigenvalue equation of psi, it's eigenvalue equation of operator O. And lambda is defined as eigenvalue of the operator O. Again, either it is eigenvalue equation or it is the eigenvalue. All are of operators. Though we are operating on the same function psi. Here exactly the concept to be understood is whenever you have an operator such that after operation it gives you lambda into psi, then this is known as eigenvalue equation and has got its own quantum mechanical significance. So operator operating on psi, some constant into psi, and very soon we'll come to know that is operator and lambda related to each other. In total, for the time being, this is known as eigenvalue equation of the operator O, and lambda is defined as eigenvalue of the operator O again. That means everything is connected to operator. Let's move ahead with some more operators. Let have some more operators. Let me call it as operator O3 as eta h cross del by del t. This will give equation number 7. Similarly, there is one more operator O4, which is minus eta h cross del by del x. That is equation number 8. There is one more operator O5, which is minus h cross square del square upon del x square upon twice m. This I am calling equation number 9. And let's consider the most generalized form of the operator, of the wave function, equal to a e raised to minus I omega t minus kx. If you see very carefully, assume it's representing a subatomic particle, and we know in a particle concept, subatomic particle rather, we have got a dual concept. It behaves like a wave also, behaves like a particle also. This A exactly is the amplitude of when you take the wave-like behavior and gives the probability of the particles to be available at any position x at any time t. So this expression exactly have the complete information of the particle we are talking about. It contains its omega, it contains its k will be connected to momentum, omega will be connected to energy, k will be connected to momentum, it's having its position and time. So it's very simple. If somebody asks you to come to college and don't mention the time, so x will be there, but time is not there. If somebody say come at 12 o'clock, but doesn't tell you the location. So to have precise meeting of a person, we have to have its position as well as time. So this is basically how we represent quantum mechanical systems, where we assume that psi contain all the information about that particular system or particular particle. Let's operate equation number 10 on O3, O4 and O5 and let's see what interesting results we get. So when I operate O3 on psi, exactly it is eta h cross del by del t of a e raised to minus eta omega t minus kx, I need not to tell O3 when operating on psi. This derivative exactly gives me, it is respect to time. So this part only get affected. But the function itself being e raised to, first e raised to derivative and integration remains same. And then respect to time will have this part to be differentiated. So time, respect to time will differentiate only minus I omega. If you see very carefully, it's O3 psi equal to eta h cross into minus eta omega, and I need not to tell the remaining term is nothing but psi. So we again got O3 into psi equal to, it's this eta is exactly as when you find under root of minus 1, it's eta. So this is what this eta is. So when I square eta, I will be getting minus 1. So this eta into this eta gives you minus 1. This eta into this eta gives you minus 1. Minus sign is already existing there. This becomes minus minus, so it becomes h cross omega psi. This I call, let me call this as equation number 11, and let me call this equation number 12. This is a very interesting thing here. This is your eigenvalue and this was your operator. If you just remember, O3 was nothing but eta h cross del by del t, implies that this is total energy operator, because I am getting total energy out of this. So what you have to understand here is, whenever we have got these eigenvalue expressions, then this eigenvalue is exactly related to, connected to the operator. Rather, the eigenvalue is a precise measurement of the operator to what it corresponds to. Assume it's energy, that means it was the energy operator. If it's momentum, it will be a momentum operator. If it's kinetic energy, it's a kinetic energy operator. Because in quantum, we follow the concept of operators. Let me take the other example. O4 operated on psi, which is exactly eta h cross with a minus sign del by del x. And when it is operated, I'll be getting e raised to I omega t minus kx. Now this is simple. O4 when operating on psi gives me minus eta h cross will be there as it is. Now when I differentiate this expression, this being exponential term, a e is to minus eta omega t minus kx will be there as it is. And then differentiation of this quantity with respect to x. So we can have eta k, minus minus become plus, it is simply eta k. There is no minus because minus minus become plus. So we can have this term will not be there, it's only eta k. So eta k. Let me put a small bracket, it looks better. So O4 when working on psi equal to, now this eta and eta become eta square, which is minus 1, this minus get nullified with the minus sign. I get h cross k. I need to tell this is my psi. This I call as, let me call this as equation number 13, and let me call this equation number 14. So the interesting thing here is very clear that this quantity is nothing but momentum of a subatomic particle, and this has to be an operator corresponding to momentum. So again, we got an eigenvalue equation where there is an operator, there is eigenvalue, there is a precise relation between this quantity, h cross k, and this operator. Since this is momentum, this is momentum operator. Let's move ahead with the next operator, psi, which is nothing but minus h cross square del twice m del square upon del x square, and its psi means what? A e raised to minus eta omega t minus kx. Now let us see what it comes out to be. It is nothing but minus h cross square upon twice m del by del x of, if I operate this function once, I will be getting a e raised to minus eta omega t minus kx, and obviously the derivative of this quantity with respect to x, so it comes out to be again k, and to be precise it is eta k. If I do the derivative once more, I need not to tell, I will be this quantity again, so it will be minus h cross square upon twice m eta k the whole square and a e raised to minus eta omega t minus kx. Again, I need not to tell, there is a slight mistakes here. This will be with a psi, and here also it is better to have the psi here equal to and psi here equal to, right? It looks more convincing. And O5 operator 5 into psi gives me nothing but this eta square gives me minus 1, minus become plus, it is h cross square k square upon twice m into psi. And this I can call it as, let me call this as equation number 15. So this comes out with nothing but equation number 16. Again, you can see this is the eigenvalue, this is an operator, this complete is eigenvalue equation, and it is very clear that though psi remains same, but when the operator changes, this value changes. Truly speaking, this is kinetic energy of a subatomic particle, and hence we come to know this is nothing but kinetic energy operator. So far we have got three different operators. One was O3, one was O4, one was O5. Respectively, this was total energy operator. This comes out to be nothing but momentum operator, and this comes out to be nothing but kinetic energy operator. Now let us have a very basic concept which I don't know whether you are aware or not. We know from Planck formula h nu, which can also be written as h upon 2 pi into 2 pi nu, which is exactly h cross. This value is h cross and this value is omega. So I'll call this expression as expression number 17. Similarly, we have an expression for P equal to h upon lambda from de Broglie, which can be written as P equal to h upon 2 pi into 2 pi by lambda. This quantity is exactly h cross. This quantity is represented by k. This is expression number 18. You can clearly see this is energy, this is momentum. Right. Further, we know kinetic energy is expressed as half mv square, which can be written as half m square v square upon 2 upon m, which gives me nothing but p square upon twice m. But from upper expression, p nothing but h cross k, so it is h cross k square upon twice m, and hence it is the expression for kinetic energy. The quantum mechanical terms which we are supposed to be aware. Actually, before having the concept of eigenfunction and eigenvalues, Let me have one more introduction. In classical mechanics, Hamiltonian is written as kinetic energy plus potential energy. Let me call expression number 20. Now, in terms of operator, we write it as like this. Expression number 21. Now, let me say a very important thing here. We are aware of this expression, which is known as Heisenberg's uncertainty principle. Is greater than equal to something like that, but I think the concept is what exactly? It says that if position of a particle can be determined, there is uncertainty in the momentum. And if momentum can be determined, then the uncertainty in the position. That means x and p cannot be determined simultaneously. So what is the big in that? Now we know a simple expression Hamiltonian is kinetic energy plus potential energy. Let us take a very simple example of a harmonic oscillator where kinetic energy can be written as p square upon twice m and potential energy can be written as half k x square. That is expression number 24. It is very clear that for a harmonic oscillator, the total energy is summation of kinetic energy plus potential energy, which is exactly determined by position of the particle and momentum of the particle. But here you can see, according to Heisenberg principle, which is available and which is valid rather for a subatomic particles, position and momentum cannot be determined simultaneously. That means this formula is no more valid for a subatomic particle. Implies classical formula fails for subatomic particles. Subatomic particles, we mean electron, proton, neutron, and so on. If this is not possible, then we use the concept of operators, which is discussed in detail all over again in the above topic, in the above exercise, I can say. Now, as far as quantum mechanics is concerned, what we actually do, we represent any function by psi. We apply some appropriate boundary conditions and we solve the Schrodinger equation of the particle. What is Schrodinger equation exactly? Again, let me call it as H equal to T plus V. This represents potential energy, this is kind of this is the total energy. In terms of operator, it will be like this. Now we already know this can be replaced by eta H cross del by del T equal to, this can be replaced because of the kinetic energy, minus H cross square upon twice m del square upon del x square plus potential energy operator represented by V only. Right? So this exactly has no meaning of its own because they are only operators. So we need to put some function which is operating on them. should be del t equal to minus h cross square del square upon twice m del x square will be again psi plus v psi equal to 26. This gives me total energy, this gives me kinetic energy, this gives me potential energy. Truly speaking, this what we got now is exactly Schrodinger equation. Since it is one dimension and it is depending on time, so it is time dependent one dimensional Schrodinger equation. Had it been this replaced by del square, then same expression becomes for 3 dimensions. So what we do in quantum mechanics exactly? We take the function psi respective to any system, maybe a particle in a well, particle in a potential barrier, particle in a potential height, particle in a potential step. We solve it and finally we get different results. There is a transmission possible, there is a reflection happening, there is a transmission plus reflection both, and so on. And when we take this operator in a spherical polar coordinates and we make this expression time independent, that means it will be simply E psi. Then the same expression can be used to solve hydrogen atom problem. This is what I feel is a brief introduction of quantum, and one should understand what exactly and how exactly the concept of operator started. I hope I was able to reach you through my lectures. Thank you.